What if I told you that the universe is being torn apart by an invisible force, and scientists are racing to understand why? Imagine a balloon with galaxies painted on its surface. As we inflate it, the galaxies move apart from each other, not because they're moving, but because the space between them is expanding. For decades, scientists assumed that the universe's expansion, which began with the Big Bang, would gradually slow down due to gravity. Just like a ball thrown upward, eventually slows and falls back to Earth. But in 1998, two teams of astronomers made a discovery that would shake the foundations of physics. By studying distant exploding stars called supernovae, they found something impossible. The universe wasn't slowing down at all. It was speeding up. This acceleration means that galaxies aren't just moving away from each other. They're moving away faster and faster as time goes on. This discovery broke every rule we thought we knew about gravity and the universe. Gravity should be pulling everything together. Instead, something mysterious is pushing everything apart with increasing strength. This force would come to be known as dark energy, the most abundant yet mysterious substance in our universe. Today, we know that dark energy makes up about 68% of everything in the universe. Yet we still don't know what it is, making it one of the greatest mysteries in modern science. To understand dark energy, we need to first understand how it's fundamentally different from any other force we know. While gravity pulls objects together and gets weaker with distance, dark energy does the exact opposite. The further apart things are, the stronger it pushes them apart. Think of dark energy like an invisible rubber band that connects everything in space. But unlike a normal rubber band that pulls things together, this cosmic rubber band pushes things apart. And the more it stretches, the more powerful it becomes. Dark energy isn't just a force. It's actually creating new space between galaxies. Every cubic meter of space contains a tiny amount of dark energy. As the universe expands, more space is created, which means more dark energy, which creates even more space. It's a self-feeding cycle of expansion. We can't see dark energy directly, but we can measure its effects by studying how light bends around massive objects in space and how galaxies move within their clusters. One leading theory suggests dark energy might emerge from the strange world of quantum mechanics. At the smallest scales, space itself isn't empty, but buzzing with particles that pop in and out of existence. Some physicists believe this quantum activity might be creating the pressure that drives cosmic expansion. While dark energy seems weak in everyday life, across cosmic distances, it becomes the dominant force in the universe, overwhelming gravity's influence between galaxies. Perhaps most puzzling is that dark energy seems to defy one of physics' most basic principles: the conservation of energy. Despite our most advanced technology and decades of research, dark energy remains as mysterious today as when it was first discovered. We can measure what it does, but we still don't know what it is. The James Webb Space Telescope has revolutionized our understanding of dark energy, and not in the way we expected. This incredible image from Webb shows us galaxies as they appeared over 13 billion years ago. By studying their light, we can trace how the universe has expanded throughout its history. When Webb looked at these ancient galaxies, it found something surprising. Their distances and speeds didn't match our predictions about how dark energy should behave. This discovery deepened what astronomers call the Hubble tension, a major conflict in how we measure the universe's expansion rate. Different methods of measuring cosmic expansion give us different answers. Webb's unprecedented clarity has made this discrepancy even more apparent. When we measure nearby galaxies, we get one expansion rate. But when we look at the early universe, we get another. These numbers should match, but they differ by about 10%. To understand these conflicts, we need to look at how Webb acts as a time machine. Light from the most distant galaxies Webb observes has been traveling for over 13 billion years. By measuring how this light has stretched, we can track the universe's expansion history. As space expands, light waves stretch out, becoming redder. The amount of this redshift tells us precisely how much space has expanded since the light began its journey. These new observations suggest our models of dark energy might be too simple. Instead of being constant throughout space and time, dark energy might be more dynamic, changing its behavior as the universe evolves. As Webb continues to gather data, we're learning more about dark energy every day. Hit subscribe to stay updated as we explore more cosmic mysteries and break down the latest discoveries from space. If dark energy continues to grow stronger, our universe could face a dramatic and violent end called the Big Rip. Scientists have identified 3 possible fates for our universe. It could freeze, expanding forever but slowing down. It could crunch back together, or it could rip apart. The Big Rip scenario occurs if dark energy becomes so powerful that it overcomes all other forces in the universe, even the forces holding matter together. If the Big Rip happens, it would follow a specific sequence of destruction. First, galaxy clusters would be torn apart. Then, individual galaxies would be shredded. Solar systems would be next, followed by planets. And finally, even atoms would be ripped to pieces. In our solar system, we would see the outer planets ripped away first. The space between the Sun and Earth would stretch faster than light itself, severing our connection to our star. In the final minutes, Earth itself would face a spectacular end. The planet would be stretched like taffy, its atmosphere stripped away, the crust cracking, and finally, the entire world would be torn apart at the atomic level. But there's good news. If the Big Rip is coming, it's still very far away. Current measurements suggest that if the Big Rip happens, it won't be for at least billions of years. Some estimates put it as far as 100 billion years in the future. We're watching dark energy's behavior carefully. Any change in its strength could tell us which cosmic fate awaits us. But the Big Rip isn't inevitable. Dark energy's strength might remain constant, leading to a very different future. Dark energy doesn't just challenge what we know about space. It challenges everything we thought we understood about reality itself. Around the world, scientists are building incredibly sensitive detectors deep underground, hoping to catch the faintest whisper of dark energy's influence on ordinary matter. As dark energy pushes galaxies apart faster and faster, many are crossing beyond our observable universe forever. Like ships sailing over the horizon, they're becoming permanently invisible to us. This creates a profound problem. Information about vast regions of our universe is being permanently erased from our view. Some physicists suspect dark energy might be connected to vacuum energy, the churning quantum foam of particles popping in and out of existence in empty space. But when we calculate this energy, we get a number wrong by a factor of 10 to the power of 120. Dark energy doesn't fit into our understanding of the 4 fundamental forces. It might represent an entirely new type of force, or signal that our theories about gravity need a complete overhaul. The implications go beyond physics into philosophy. What does it mean that most of our universe is made of something we can't see, touch, or directly measure? New experiments like the Dark Energy Spectroscopic Instrument are mapping millions of galaxies, creating the largest 3-dimensional map of our universe ever made. Trying to decode dark energy's fingerprint, solving the dark energy mystery might require a revolution in physics as dramatic as Einstein's theory of relativity. We might need entirely new mathematics to describe how space, time, and gravity truly work. Understanding dark energy could unlock new technologies beyond our imagination, just as Einstein's theories eventually led to GPS satellites and nuclear power. As we peer deeper into space and time, we're faced with a humbling truth. The more we learn about our universe, the more mysterious it becomes. Thank you for joining me on this journey through one of science's greatest mysteries. If you enjoyed this exploration of dark energy, please like and subscribe for more deep dives into the cosmos. Until next time, Keep looking up and wondering.